Hello, chemistry class. In the previous section, we saw how a galvanic cell uses an oxidation reduction reaction to generate an electric current by separating the oxidizing agent from the reducing agent. In this section, we're going to look at several examples of the galvanic cell and their application, the applications of those, and primarily those are batteries. So we're going to look at some dry cell batteries, lead storage batteries, and you probably all heard of lithium-ion batteries. So if you'd like to look into those, that's advanced proficiency. You can look at how those work. So let's first look at the lead storage battery. You guys probably recognize a lead storage battery from your automobiles. That's where we see these. They've been around for a very long time, and they do a remarkable job. Basically undergoing very extreme temperatures, and especially in Gilpin County on all our rough roads, they are under constant abuse from bumping around on our dirt roads here. This is the basic reaction that happens in a lead storage battery. The reducing agent is the lead metal, and then the oxidizing agent is this lead 4 oxide right here. And in the lead storage battery, it is the sulfuric acid that provides the electrolyte solution. That electrolyte solution here is what gives these half reactions the necessary materials. Right here, it gives the hydrogen sulfate ion and the proton ions for the cathode reaction as well. So one more thing to mention about batteries is this word called potential. And you've probably heard that. You've also heard of the word volts. Potential is measured in volts. Just if you think about the tendency for electrons to flow, that's what we're talking about when we talk about the potential. How readily do electrons flow from the cathode to the anode? And it depends on the ability of the reducing agent to release electrons and on the ability of the oxidizing agent to capture electrons. And that readiness for electrons to flow through there is what we call potential. In each of the lead storage batteries, in each cell, they produce about 2 volts of that potential. And in automobiles, in an actual automobile battery, 6 of those little cells are connected to give us about 12 volts of potential. So let's take a look at another kind of battery. And these are batteries that you are very familiar with. Dry cell batteries. Calculators, electronic watches, portable radios, toys, flashlights, they use these dry cell batteries, right? They're called dry cell batteries because they do not contain a liquid electrolyte. Instead, they have this paste in here. This is the acid version. There's an alkaline version of a dry cell battery, but in the acid version, the paste is made up of ammonium chloride and a few other ingredients as well. The alkaline version replaces the ammonium chloride with potassium hydroxide or sodium hydroxide. So that would be just the difference between an acid battery and an alkaline battery. The alkaline battery also usually lasts a little bit longer because the zinc generally does not corrode as quickly. We're going to talk about corrosion in just a minute, but doesn't corrode as quickly in alkaline or basic conditions. So let's take a look at this reaction. We have our anode here, our cathode is here, is a graphite rod. The anode is this zinc inner case, and that's what's used for those. The anode reaction, remember, is oxidation. Here's our anode half reaction. Here's our reduction half reaction at the cathode, and that's what's going on. And when talking about potential, this cell usually produces a potential of about 1.5 volts. So I said we'd get to corrosion. What is corrosion, and why is that interesting to us? Corrosion is the process of returning metals to their natural states. It usually involves the oxidation of the metal. And you guys all know this, corroded metal often loses its strength and attractiveness. Sometimes we like the way it looks. Sometimes people intentionally like that corroded metal look, but oftentimes it's quite undesirable. So why, if corrosion happens, if metals exposed to air corrode and they are oxidized and they turn back into the ore, the metal ore, why doesn't corrosion prevent using metals ever in air? Why don't all metals just corrode, turn back into their metal ore, and that doesn't work very well for us, right? Why doesn't that happen? Well, the reason for this is that metals basically protect themselves from corrosion. A lot of metals do. Some are better at it than others. By providing a thin layer, forming a thin layer, like a protective layer on the outside. Aluminum is an example. Aluminum does this really well, and that's why it's used so often. It forms aluminum oxide on the outside layer of itself, and that keeps the inside of it, the atoms on the inside of that metal, from corroding. Basically, that protective layer on the outside keeps further corrosion from happening. Iron can also perform a protective oxide coating. It's not a very effective shield, though. It scales off easily and doesn't do nearly as well. You all know silver tarnish is actually silver sulfide. It's a thin layer that forms on the outside of silver. Gold doesn't show appreciable tarnish in air. So every metal is a little bit different, but that is how some metals prevent corrosion. How do we prevent corrosion? We coat the metals, right, with paint or other protective coatings. This obviously didn't, last forever, did it? The corrosion still got to that metal. Another form of protecting metals so that they do not corrode would be alloying. And this is basically mixing together different metals. For example, stainless steel is an alloy. It contains both chromium and nickel, and they form coatings, both of those, that protect the steel. And cathodic protection is another way we try to prevent corrosion in like buried fuel tanks and pipelines. And basically, the idea behind this is that a metal that furnishes electrons more easily than the iron is connected to that pipeline or that tank that we want to protect. Magnesium is such a metal. Magnesium provides electrons more easily or more readily than iron. It's a better reducing agent than iron. So the electrons flow from a magnesium wire to the iron pipe, and the electrons are furnished that way, so it keeps the iron from being oxidized. Obviously, then the magnesium needs to be replaced over time as magnesium is oxidized. So those are some ways that we can prevent corrosion. So back to our dry cell batteries. We've got some more different dry cell batteries to look at. There's the nickel cadmium battery, and you have heard these. It's a type of dry cell battery. Here's the reactions for a nickel cadmium battery. The anode reaction where oxidation is occurring. Here our cadmium is being oxidized. Then we have our cathode reaction where reduction occurs, and that's the half reaction for that. Here is a mercury battery. You've seen this shape before. Those are another kind of dry cell battery used in small calculators. So here again we see the cathode here is a steel cathode, and our anode is the zinc container itself. And then we have our electrolytic agent inside right there. Some advanced ideas. We didn't talk about lithium-ion batteries. So research those. Those are interesting things to look at. Also, the current internal combustion engine used in automobiles makes very inefficient use of energy, causes a lot of air pollution. And so one strategy that's considered is using electric cars powered by really big storage batteries. Research some of that. What do they do differently in those? What are the limitations that have been found in these storage batteries? Why are they limited? That's an interesting thing you can look into. Research any of the batteries that we mentioned more in detail and come up with more applications and how these batteries are used. And I look forward to seeing you in class.